lakes and streams. And that can cause a problem called eutrophication. So this picture right here is a nice picture of an algal bloom that has covered the entire surface of a body of water, which is what eutrophication is. And this can be very detrimental to aquatic life in that water and also a nuisance for human recreational activities. So one possible solution to prevent this eutrophication problem is to remove the phosphorus from the manure before you apply it to the cropland. And while there are many different techniques for removing phosphorus, the one I'll be talking to today about is struvite, which is a compound magnesium ammonium phosphate that can be precipitated from the manure and used as a slow-release fertilizer. So anaerobically digested manure is already very high in ammonium and phosphate, which are two of the main components of struvite. So theoretically, all you would need to do is add a magnesium source and increase the pH, since struvite solubility decreases as pH increases, and then you would be able to precipitate that phosphorus as struvite. So in swine and poultry litter, this has already been studied, and you can get up to 80 to 98% phosphorus removal, which is very high. However, for dairy, there's an additional challenge because dairy manure has a lot of calcium ions in the manure, and the calcium ions actually compete to bind with that phosphorus and form calcium phosphate, and then that phosphorus isn't available to precipitate struvite. So you have to do an extra step where you add an acid, and so you add an acid to disassociate the calcium phosphate bonds in the manure, leaving that phosphorus available for struvite precipitation. And currently, the acids used are hydrochloric acid and sulfuric acid, but these can be quite costly, and you have an added problem of when you increase the pH to precipitate the struvite, you could just have the calcium and the phosphorus joined together all over again and still have a calcium phosphate problem. So we've been looking for a different solution to remove that calcium, but also we still need an acid. So oxalic acid became a very desirable option because it has acidic properties, but it also can chelate the calcium and form a calcium oxalate compound that you can then remove from the solution, and then you would be removing the calcium problem, and the phosphorus would be available for struvite precipitation. So one problem with this, though, is concentrated oxalic acid is still expensive. And so we were looking for a cheaper source of oxalic acid to use. And we came across this fungus, Aspergillus niger, which is most known for producing citric acid for the commercial grade food industry. And they have seen often, or at least sometimes, oxalic acid produced in their systems as an unwanted byproduct. But studies were done to see what kind of conditions led to optimal oxalic acid production, and it was found that if you used a lactose substrate, then you would primarily produce oxalic acid from this fungus. And so when looking for a lactose substrate to use, we settled on whey permeate, as this is seen as an inexpensive byproduct of the cheese industry, where after you've made the cheese, you have the whey left over, and it's much more common now to process that even further and take out the whey proteins and sell them as a protein supplement. So then you're left over with this whey permeate, which is basically lactose, water, and salt. So this leads us to our first experiment, oxalic acid production using Aspergillus niger. So the objective was to produce sufficient oxalic acid, which we determined to be a 1 and a 1.5% solution of oxalic acid, for struvite precipitation using Aspergillus niger on a whey permeate substrate. And we investigated optimal factors for oxalic acid production by varying the lactose concentration of the whey permeate and the temperature. So the hypothesis was that Aspergillus niger would produce adequate amounts of oxalic acid to promote calcium removal and struvite precipitation from the manure. So our materials and methods, we did 3 different fermentations, and we used 2 different strains of fungus. The 2 different strains were ATCC 6275 and ATCC 9029. And so the cultures were grown on potato dextrose agar plates for 7 days, and then we collected the spores and used that spore suspension to inoculate 1 liter of autoclaved whey permeate and the whey permeate was in a 2-liter beaker and covered with aluminum foil and put on a hot stir plate. So this picture on the right here is an example of what that setup would look like. So the pH was adjusted daily to 6 with sodium hydroxide, and all samples were autoclaved immediately after collecting, and then we analyzed them for oxalic acid content using an assay kit. So as I mentioned, there were 3 different fermentations. So the first fermentation used both strains of the fungus, 6275 and 929, and were inoculated in a 20% lactose whey permeate maintained at 30 degrees Celsius for 14 days. So to reach the 20% lactose, we actually supplemented the whey permeate with a lactose powder that we got from Grandia Foods. And samples were collected on day 0, 1, 2, 3, 4, 5, 6, 7, 10, and 14. The second fermentation used the same 2 strains of the fungus, and this time though it was inoculated in 11% lactose whey permeate, still maintained at 30 degrees Celsius, but this time for only 6 days. So after the first experiment, we saw that there was about maximal production of around 6 to 7 days, so we decided to cut it down for 6 days for the second fermentation. And this time, the whey permeate was not supplemented, so the whey permeate without extra lactose powder was 11% lactose. And then the third fermentation, we only used the 1 strain, ATCC 9029, still inoculated in 11% lactose whey permeate, and this time it was either maintained at 30 degrees Celsius or left at room temperature for 6 days. So we selected this strain because it seemed to be possibly doing better than 6275, but also this strain had been proven to have good oxalic acid production in other literature. So we decided to just use that one. And then for the room temperature beaker, it just meant that it was still in the heating stir pad covered, we just didn't turn the heat on, and samples were collected daily. So we'll look at some of the results. So this is fermentation 1, which, if you recall, is 2 strains in the 20% lactose, 30 degrees Celsius for 14 days. So this orange line here is strain 6275, and the blue line is 9029. And you can see that while they had pretty different production patterns, they both end up at about the same level, which is around 5 millimolar oxalic acid by day 14. So this is the second fermentation. So this was an 11% lactose permeate this time. So same 2 strains, still 30 degrees Celsius, just a different lactose concentration. And this 9029 is the blue line, and this time it got up to around 7 millimolar, and the orange line here, 6275, is right around 3 millimolars of oxalic acid by day 6. And then this is the third fermentation. So this one is just 9029, but either at room temperature or at 30 degrees Celsius. So this orange line, much more linear than all the other lines we've seen, is the room temperature one. And then the blue line here still follows a similar pattern to what we'd seen before, which was at 30 degrees Celsius. So this kind of suggests that this still reached at about the 7 millimolar as the last fermentation, so it got to the same point in the end, but it took much longer. For the last fermentation, it took about till day 2 to get up that high, and this time it took it pretty much till day 6, day 5 to get up that high. So this could suggest that the heat might not be so crucial, but it can definitely shorten your lag phase in the beginning to get to your maximum oxalic acid production. So what we saw from all of these is that in all 3 fermentations we had less than 10 millimolar oxalic acid production. So if we want to compare to what that would be in the literature, sucrose media studies reported 175 to 427 millimolar oxalic acid. Glucose media studies are 48 to 321 millimolars oxalic acid. And whey media, which is very similar to what we used, except the whey proteins were still in there, is 92 to 278 millimolars oxalic acid. So you would say that our oxalic acid production was much lower than what was reported in the literature. And the question is why? And my answer is I don't know. But when we compared our results to the literature, our fermentations were conducted at the optimal temperature, 30 degrees Celsius, which was suggested by other studies. It was kept at a pH of 6, which had been proven to be the best pH for oxalic acid production. And even though I didn't touch on it in materials and methods, it was at the optimal inoculation concentration from what the literature suggested was used. So one other thing I looked at was there enough nitrogen and phosphorus for the fungus to produce oxalic acid? And studies using a whey had tested whether or not the whey needed to be supplemented with nitrogen and phosphorus, and they found that it did not. And when I compared our whey permeate to that whey, we actually had more nitrogen and phosphorus than that whey. So that did not seem to be deficient in nitrogen or phosphorus. Another problem people had seen was product inhibition. But when we tested our whey permeate at the beginning, there was no oxalic acid content present initially, so that should not have been a problem. So a few possible explanations that I've been able to come up with was maybe the high concentration of salt. As I mentioned earlier, whey permeate is mainly lactose, water, and salt. And there are studies looking at other organisms where salt has had an impact, negative impact on fermentation. But I also found a study specifically using Aspergillus niger where it actually increased the production of Aspergillus niger to have higher salt concentrations. So I'm not quite sure on how the salt would play a factor, but it is possible that it was negatively impacting fermentation. Another possibility could be contamination. We did autoclave the whey permeate when we first used it, but interactions with the media after that were probably not as sterile as they should have been. So it's possible something else got in. Also, we measured the total amount of acidity produced, and not all of it was explained by oxalic acid. So there could be another organism possibly producing something like gluconic acid if it used lactose in a different way, because studies looking between the different medias with this fungus, if you had the lactose substrate, it doesn't produce any gluconic acid at all, which makes me think that it must be another organism. Another possibility is if it was redirecting the resources to biomass production. So there were also some studies that suggested if you had high amounts of trace metals, nitrogen, phosphorus, that it might redirect to biomass production rather than producing secondary compounds like the organic acids. So that could also have played a factor. And an interesting thing to note is that some students at Oregon State University, before we did this experiment, did a very similar experiment and found that they also barely got any oxalic acid produced. And at the time, I was questioning some of the methods that they used. They weren't necessarily ones that the literature supported, so I thought we would be able to rectify that problem, but clearly we still got similar results, so there must be something else going on here. So from this first experiment, the idea was to collect that media with the oxalic acid solution and use it in the next experiment to add it to manure and remove calcium and produce struvite. However, since we did not produce enough in the first experiment, we decided to instead use commercial grade oxalic acid and continue on from there. So that leads us to the second experiment, struvite precipitation from anaerobically digested AD dairy manure. So the objective was to remove phosphorus from AD manure's precipitated struvite and investigate optimal pH conditions for struvite precipitation by varying the pH at the acidifying step and the precipitation step. Also investigate the effectiveness of adding oxalic acid on calcium removal. So the hypothesis was adding oxalic acid would lead to high calcium removal from the manure, and the greatest phosphorus removal as struvite would be achieved at the lowest pH for the acidifying step combined with the highest pH at the precipitation step. And these steps that I'm talking about will become more clear when I show you the experimental design. So for the materials and methods, we use anaerobically digested manure collected from the Vanderhoek anaerobic digester. The manure was first acidified with hydrochloric acid to one of three pHs, 5, 5.5, or 6, followed by the addition of the commercial oxalic acid, so that was to remove the calcium. And then you add the magnesium source I mentioned before you need for struvite, and increase the pH, which you also need for struvite, and then we decided to vary to three different pHs, 7.7, 8.2, and 8.7. So with all of that together, there were 9 treatments with duplicates, and 1 liter of manure was the sample size. So oxalic acid, we added it in a 1-to-1 molar ratio of oxalate to calcium because we wanted that oxalate to bind with the calcium and remove it. And magnesium chloride was added at a 1.5-to-1 molar ratio because while 1-to-1 is all that you need for struvite precipitation, there were studies indicating that higher ratios, slightly over 1-to-1, would give you actually more struvite precipitation. So that is the ratio we chose. And data was analyzed as one-way nodal with approximate sense. So here is a simplified flow diagram to hopefully better illustrate what exactly I did. So here on the left, you have your raw manure. And the first thing you do is add that acid. That's to break the calcium phosphate bonds apart. And this is where we changed it to either 5, 5.5, or 6. After that, we'll centrifuge it. And then from there, you end up with a sludge and a supernatant component. And this picture on the right here is to hopefully illustrate what I'm talking about, where this kind of pasty looking substance there is the sludge and the rest of the liquid in the bottle is the supernatant. So I tried my best to separate those two. So here in the first sludge, you are mainly expecting, are there any solids that weren't separated when the manure went through a solid liquid separator? And then if you were not able to completely disassociate the calcium phosphate bonds with the acid, then you would have some calcium phosphate that would also be lost into the sludge. So we'll move through the rest of the process with supernatant 1. So now we're hoping we have free-floating calcium and phosphorus in our supernatant for struvite precipitation. And then we'll add the oxalic acid in hopes that the oxalate binds with the free-floating calcium to form the calcium oxalate. And then once we centrifuge that, if there was calcium oxalate, it would all end up in this sludge tube here. And you'd be left with the supernatant 2 that now has free-floating phosphorus and is hopefully low in calcium. So from there, you just add some magnesium chloride as a magnesium source, increase the pH with the sodium hydroxide to either 7.7, 8.2, or 8.7, and then centrifuge again. And so if you were successful in precipitating struvite, it would be in your sludge 3 here. And if not, then you would have a lot of phosphorus left over in your supernatant 3. So here's another thing to try to hopefully illustrate what happened with all these different pHs I'm talking about. So if you can imagine that we had 9 treatments, 3 of them got acidified 5, 3 to 5.5, 3 to 6. And then in the middle here, in between steps, we've added the oxalic acid, and then you have the magnesium chloride before you change the pH, increase it to 7.7, 8.2, or 8.7. So, for example, this flask here in the bottom left corner, its pH code would be 5.0/7.7 for that treatment. And then everything was done in duplicates. So now we'll look at the results. So this is the results of orthophosphorus levels and total phosphorus levels in supernatant 1. So orthophosphorus is that free kind of floating phosphorus I was talking about before. Total phosphorus includes orthophosphorus, any organic phosphorus that's in there, and if there's still some inorganic compounds like calcium phosphate, we would include that too. So here, the letters are a little confusing, but the letters, if they are different from each other within the same line, then they are significantly different. So this orange line up here is the total phosphorus, and the blue line is the orthophosphate. So as you can see, samples at pH 5 and 5.5 were significantly higher for both orthophosphorus and total phosphorus than the samples at pH 6. And this is what we would expect, because this is suggesting that pH 6 wasn't low enough to separate those calcium phosphate bonds, so that some of the calcium phosphate was still in solution. So when we centrifuged the sample, it ended up in the sludge, which would mean that you had a lower amount of phosphorus in your supernatant. So now we're looking at supernatant 2. So now all we've done is we've added the oxalic acid, hoping to remove the calcium, and centrifuged again. So here we see the same pattern, where this is the total phosphorus and this is the orthophosphorus. And again, pH 5 and 5.5 is significantly higher than the samples at pH 6. So this is really just a pattern that's carried over from the first step. The phosphorus levels don't really change all that much when you've just added oxalic acid. So this is again just because some of that calcium phosphate was lost in the sludge one. So So this is looking at our change in calcium over these steps that we've done. So here we have how much calcium we had to start with, and then in the middle this is supernatant 1. So as you can see, the calcium went down a little bit for all the treatments, and that would be from both sending subsamples to the laboratory for analysis, but also you lose a little bit when trying to separate the supernatant from the sludge. It's not a perfect process, and my supernatant gets lost with the sludge. But as you can see, it had the same pattern as the phosphorus, where pH 5 and 5.5 were significantly higher in calcium than a pH of 6. So that, again, is explained by the same principle that the calcium phosphate, the pH wasn't low enough to disassociate that, so the calcium phosphate was precipitated out in the sludge 1, which would lead to lower calcium in this sample, in the supernatant 1. And then as you can see on the right here, supernatant 2, our calcium levels have gone down quite a bit. So that is, we've added the oxalic acid and then centrifuged again. So this is definitely illustrating that the oxalic acid is doing what we wanted it to, where it bound with the calcium, formed calcium oxalate, so that when we centrifuged it, all that calcium oxalate got captured in the sludge tube. And we're left with the supernatant that's now very low in calcium. And here, the treatments were not, there wasn't really that much difference in the amount of calcium at that level, as probably because when we were adding the oxalic acid, you might recall I wanted to add a 1-to-1 molar ratio. However, we were basing that off of a calcium value from preliminary results in manure, and then when we actually ran it, it turned out that calcium was not a lot lower, but it was lower than we thought. So the ratio that we added was much higher. So excess of calcium, or oxalate ions. So that would probably eliminate any differences you'd see between the treatments, since there was an excess. So supernatant 3, so now we've acidified the manure, we added the oxalic acid, removed the calcium, and now we've added the magnesium chloride and increased the pH so that we can precipitate struvite. So now that's why you'll see the different pH codes I mentioned before. It has what they were acidified to as well with what they were increased to at the end here. And again, the letters are a little confusing, but you would stay with the same color. So all the orange bars, the letters are compared to each other, along with the blue bars, where the orange is the total phosphorus and the blue is the orthophosphorus. So here, what we would like to see is a supernatant that is low in phosphorus, because that means the phosphorus was precipitated as struvite and captured in the sludge. So as you can see, these treatments on the left that had the highest amount of phosphorus were all increased to pH 7.7. So that indicates that that pH was not high enough to promote the struvite precipitation that we wanted. The pH 8.2 is kind of in the middle here, where the 5.5, 8.2, and 6.0, 8.2 still doing better. Looks like they had more struvite precipitation. And then on the end here are all the ones that were raised to 8.7. So that was indicating that that pH was definitely high enough to remove the phosphorus from the solution. And this is the counterpart to that, the sludge. So we're seeing the same pattern here, where on our 7.7 treatments, there's not a lot of phosphorus. That's because it was still in the supernatant, wasn't precipitated as struvite. And then on the right, on our 8.7 treatments and some of our 8.2 treatments here in the middle, were definitely much higher in phosphorus, indicating that those pHs were able to influence the precipitation of struvite. So this table is estimating how much phosphorus was removed from each treatment, from the very start of the manure to that supernatant 3, which is now hopefully low in manures, or low in phosphorus, so that you can apply to the crops. So here, our top 3 are the pH 7.7s, and they had our lowest amount, 55, 16, 63% phosphorus removed. 8.2 is in the middle, with 70, 80, and 87%, and 8.7 was at the high end with 88, 89, and 90%. So from this experiment, we saw that the oxalic acid removed about 97% of calcium from all the treatments, indicating that it did the job that we wanted it to do, which was remove the calcium so that it wouldn't inhibit struvite precipitation. And that agrees with what we see in the literature, where reports have gotten anywhere from 90 to 100% their calcium removed with oxalic acid. We also saw that lowering the pH to 5 is not necessary, since pH 5.5 and 5 were not significantly different from each other and the amount of phosphorus that was in solution compared to pH 6. So that would save you some money if you didn't have to lower the pH all the way to 5. And we saw that increasing the pH to 8.7 led to the most phosphorus removal. However, once you get above the pH of about 8.5, you start having magnesium phosphates complex out, and so you would have the phosphorus removed, but it wouldn't be pure struvite. So with all this in mind, we recommend the treatment 5.5, 8.2, because then you won't have to spend as much money lowering the pH all the way to 5, get the same results, and then 8.2 will allow you to still get a fairly high phosphorus removal with 80%, however you're avoiding that magnesium phosphate problem. So if we compare this to what the literature has, Zhang et al. 2010 used EDTA, which is a different kind of chelating agent, to bind calcium, and they recovered 70 to 82% of the total phosphorus as struvite. However, the amount of EDTA that they needed to add to achieve this, the authors agreed that this was fairly infeasible for commercial production. Shen et al. Used oxalic acid and a pH of 7.2, and they recovered 92% of their orthophosphorus as struvite. So as you may recall, orthophosphorus is that free-floating struvite, so it would be more useful if they actually reported a total phosphorus, because it's very easy to recover as much of your free-floating phosphorus as possible. So it's very difficult to compare our results with theirs. Other authors used microwave digestion of oxalic acid and recovered 95% of their total phosphorus as struvite, where microwave digestion is something that would replace the anaerobic digestion step. So they recovered a lot of their phosphorus as struvite. Those studies show that the microwave digestion may be able to release more of that total phosphorus as orthophosphorus compared to anaerobic digestion. And so if it is able to convert more of that total phosphorus to free-floating phosphorus, then it is very likely that they would be able to achieve a higher total phosphorus removal with that. And Zhang et al. Again used microwave digestion and oxalic acid and recovered about the same amount. And they did it at a much lower pH than we did, which is theoretically possible since they had more orthophosphorus to work with. So now we're going to switch gears a little bit to go to my third experiment, because while we've been talking about taking oxalic acid and making the struvite, now we're going to talk about how struvite performs as a fertilizer, as specifically a slow-release fertilizer. So a little bit of background. Struvite is often comparable and superior to other commercial phosphorus fertilizers, especially, and has been tested in fruit trees, ornamental plants, and crops. And it's especially reported to perform comparably when used in acidic soils. However, the reports for alkaline soil are a little bit more contradictory. So we have some studies saying that struvite is superior to ammonium phosphate fertilizers, comparable, and some even say that they're inferior. And so we wanted to design an experiment to really clarify this relationship between struvite and the different pHs in the soil. So that led to the third experiment, agronomic comparison of struvite versus monoammonium phosphate. So the objective here was to compare the dry matter yield, concentration of phosphorus, and phosphorus uptake in a triticale crop fertilized with either struvite or MAP by varying the fertilizer application rate and the soil pH. So our hypothesis was that struvite will be comparable to MAP for dry matter yield, concentration of phosphorus, and phosphorus uptake in both acidic and in the alkaline soils. So in materials and methods, we investigated two different treatment methods with this: the soil of the pH of the soil and the fertilizer application rate. So the soil was collected from an organic farm and it had an original pH of 5.9. So in order to test different levels of pH, we added lime to the soil, and then our final soil pH levels were 5.9, 6.8, and 7.0. And then we applied either struvite or MAP at rates of 0.56 or 2.4 kilograms of P2O5 per hectare. And later in the presentation, you'll see these referred to as the control, S56 and S224 for struvite, and M56 and M224 for the MAP treatments. And altogether, this led to 15 treatment combinations with triplicates for a total of 45 pots. And the data was analyzed as a two-way ANOVA and SAS using ProcMix. So a little more materials and methods. We planted 9 seeds of triticale per pot, and we applied urea at 90 kilograms nitrogen per hectare so that nitrogen was not a limiting factor, since we really wanted to focus on the effects of phosphorus. And triticale was harvested twice over a 45-day period, and both of those harvests were combined into one sample and analyzed for dry matter yield, concentration of phosphorus, and phosphorus uptake. So this picture on the bottom here, these short plants here, those were all my plants, and they were housed in a greenhouse, as you can see, for the duration of the study. And I'm going to take a brief second here to mention one of my friends that I ran into on my study. As you can see in this picture, it's a little hard with the lights on. In the far corner there is a frog in my plant. So on my first harvest, I went and I was checking all of my plants to make sure everything was okay, and I found this frog there. And I had the undergrad who was helping me remove that frog because I did not want to touch it. And it was on the weekend. I didn't know if there were supposed to be frogs in the greenhouse. Nobody was around, so I left a note on the door saying, hey, I found this frog. I took it outside. I don't know if there are any more. Then I went the next day, and someone had replied to the note on the door saying, that was Hank. Hank had been staying here in the greenhouse during the winter, but it was probably time for he or she to move on. So this is in memory of Hank, because it snowed a few days later after that, so I don't know what happened there. So I'm sorry, Hank. So now we'll look at the results. Oh, those boxes. Well, that's unfortunate. All right. Well, this table is showing the different factors where there was no interaction between fertilizer application rate and the soil pH. So that included dry matter yield, phosphorus uptake, crude protein uptake, the concentration of magnesium, and the magnesium uptake. So these boxes are supposed to be over these bolded letters here, numbers, to show that M224 here had the highest amount for all of these factors: dry matter yield, phosphorus uptake, crude protein uptake, magnesium concentration, and the magnesium uptake. So M224 is the highest rate of the MAP fertilizer. Helps you, they're good. All right. So this table is for the concentration of phosphorus. So this shows that there was an interaction between the pH of the soil and the fertilizer application rate for this vector. And as you can see here, S224 and M224 were comparable and had the highest amounts of phosphorus concentration for all 3 different soil pHs. This table is for crude protein, the concentration of crude protein, and it also had an interaction between soil pH and the fertilizer application rate. These ones are a little more all over the board. As you can see for pH 5.9, we have the control, and S224 have the highest concentration of crude protein. At 6.8, we have the control again, S224 and M224, and at pH 7, we have the control, S224, and both rates of the MAP fertilizer. So this would indicate that there really wasn't an impact from the treatments on the concentration of crude protein, since the controls were right up there with the highest amount. But this was what we expected. We applied urea to all the pots to eliminate nitrogen as a limiting factor, so this is within reason. So what we saw from this experiment, we saw that MAP was superior to struvite for dry matter yield, phosphorus uptake, crude protein uptake, concentration of magnesium, and magnesium uptake. So, and we also saw that for these factors, there was not really an effect from the pH of the soil. So we could expect this dry matter yield response because it's been seen that a higher amount of phosphorus availability at the beginning of the planting phase leads to a higher dry matter yield at harvest. And so commercial fertilizers are designed to have readily available phosphorus as soon as you apply it to the land. However, struvite is a slow-release fertilizer. As you can see here, where Duke Grice et al. Found that only 20% of their struvite had dissolved in the first few weeks. So if you're not having as much phosphorus available at the beginning of the planting, then you might end up with a lower amount of dry matter yield compared to the commercial fertilizer. And then that would also kind of explain what happened with the phosphorus uptake and the crude protein uptake, because those values are calculated with yield in mind, and since it was already superior in dry matter yield, that also influenced your crude protein uptake and phosphorus uptake values. The magnesium was a little bit more surprising because there is magnesium in struvite, and so you would expect that the plants that received struvite to have a higher concentration of magnesium. However, when we look back at the soil was actually really high in magnesium all by itself. So that alone kind of confounded any results you would get from magnesium between the treatments. We also saw that there was a minimal effect from fertilizer on the concentration of crude protein. And again, we expected that since we applied nitrogen to all of the pots to eliminate nitrogen as a factor. And then we also saw that struvite was comparable to MAP for concentration of phosphorus for all three soil pHs, both in the acidic and the alkaline soils. So we predicted struvite to be comparable to MAP in the acidic soil because, as I may have mentioned before, struvite solubility increases with decreasing pH. And that would mean greater phosphorus availability for the plant as the struvite is degrading. And there are many studies here that have found struvite to be comparable or superior to commercial fertilizers in acidic soil. However, DeGrice et al. Recently found that struvite processing and application method can actually have a greater impact than the soil pH on how struvite performs. And they did an experiment where they ground struvite and MAP and mixed them throughout the soil, and found that they were comparable for dry matter yield, concentration of phosphorus, and phosphorus uptake in both alkaline and acidic soils. However, when they did the same thing with granular struvite and MAP and mixed them through the soils, the struvite performed inferior to MAP in both the acidic and the alkaline soils. And so part of this is because you have increased your smaller particle size, you having greater contact between the surface area of the fertilizer and the surface area of the soil, which leads to more phosphorus adsorption and increased phosphorus availability to the plant. It's where you have granular struvite that the soil pH becomes much more of an important factor. As you can see, they did an experiment where 40% of their struvite had dissolved after 4 weeks in acidic soil, but only 3% dissolved after the same amount of time in an alkaline soil. So when you have a small particle size, the pH is not really that much of a factor. However, if you're applying granular struvite, it makes a very large difference in how the struvite will perform. And all those studies that I mentioned on the previous slide that said struvite was so great did grind their struvite and mix it into the soil. So that explains partially why they would see struvite to be comparable and even superior to the commercial fertilizers. In our study, the struvite was lightly crushed, so it did have a smaller particle size. So that might explain why we didn't really see an effect from the pH. As I mentioned, the granular is really where that pH plays a large factor. However, instead of mixing it through the soil, we actually applied both the struvite and the MAP in banded application just under the soil surface. So you wouldn't have as much fertilizer surface to soil surface interaction as if you completely mixed it through the soil. So that might explain why we did not see comparable dry matter yield and phosphorus uptake even in this acidic soil. So now to go over the conclusions to kind of wrap those 3 different experiments back together. In the first experiment, we found that Aspergillus niger fermenting whey permeate produced very small quantities of oxalic acid, and it was for relatively unclear reasons. In the second experiment, we found that the oxalic acid removed 97% of our calcium from the treatments, which is what we would want for a good struvite precipitation. And we recommended acidifying the manure to 5.5 to get that adequate dissociation from the calcium phosphate bonds, but also you wouldn't need to increase your cost by going all the way down to 5. And recommended increasing the pH to 8.2, as that still gave very good levels, 80% phosphorus removal of struvite, but then you're avoiding any of that magnesium phosphate complexing that could give you impure struvite. And from the last experiment we just talked about, we saw that struvite was comparable to MAP for the concentration of phosphorus. However, MAP was superior for dry matter yield, phosphorus uptake, and a couple other variables for triticale in all 3 of the soil pHs. And we think maybe a combination of the small particle size we used and the banding application is why we saw the results that we did. So some future research ideas that I've come up with. At first, I would say a side-by-side fermentation comparison of whey versus whey permeate would be good, because whey has already been in studies shown to have very good oxalic acid production. So that way you could at least prove that your setup is not the problem if the whey still produced good oxalic acid. And also comparing whey permeate versus demineralized whey permeate, which is just whey permeate that has had its salt content reduced, to see if salt is really actually causing a problem with oxalic acid production. And then hopefully that would help clarify if we really can use whey permeate as a substrate for oxalic acid production. And then once you have enough oxalic acid from the fermentation media, I would suggest comparing it to the commercial oxalic acid like we used in the second experiment to see if it still performs the same way, even though it was made from the fermentation, and see if it can still, produce sufficient struvite precipitation. And then for the last one, this is actually already a future research that is going to happen, but there will be a field experiment comparing ground struvite and MAP with granular struvite and MAP, and the application methods on dry matter yield concentration and concentration of phosphorus and phosphorus uptake in alfalfa. So I think that will, better clarify what processing needs to happen or the application method necessary to get good results from struvite. So with that, I would like to thank a couple people for this very long journey. I'd like to thank my advisor, Joe, for, even though he wasn't here most of the time, he was here in spirit, helping me and supporting me through my research and studies. My committee, Amber and Dr. Fox, I'd like to thank them too for all of their support and their help, and Amber especially, there you are, lost you, for letting me use the lab and all of your resources. That was very helpful. The department chair, Dr. Johnson, she couldn't make it today, but she was also a great help in making sure I got done what I needed to get done. I'd like to thank the entire Department of Animal Sciences for letting me do my master's program here, and especially the staff in the front of the office. They are supremely helpful with getting all the administrative stuff that I don't know how to do done. Very helpful. My fellow animal science graduate students, a lot of them are not here anymore. That used to be with me when I first got here. I've been here for so long, but they're here in spirit, especially Jacob, who was my previous office mate and has already made his way out of here. But he was very supportive and a great friend. And Sophie, who is here today, for being a great friend and supporting me and watching Disney movies with me. Always good. The Washington State Dairy Products Commission for funding my research. Couldn't have done it without them. My coworkers at FDIU, some of them are here, a few of them, for being understanding that I needed time to complete this, even though I still had another job. And last but not least, my friends and family, my parents who couldn't make it here today, and my other family members, very supportive and loving, and my husband, who did make it here today. Thank you for supporting me through all my mental breakdowns, trying to get this together. And with that, I would like to answer any questions.
Okay, Katie mentioned that she did get support from the Washington State Dairy Products Commission, so they provided about $20,000 in support, which helped on the first two experiments. And then we've also we received a federal grant of $500,000 earlier this year. It's helped out with the third experiment. So the other thing that I didn't mention was that Katie is a part of her scientific writing class. Took about 6 years worth of research that we conducted on agronomic aspects of struvite. They were conducted by different people, different locations. She took all that data and put it into manuscript form, so she really learned what it was all about in terms of scientific writing, and that manuscript was accepted last year for publication, so she's already an author. So we'll open up for questions now, either from Puyallup or here in Pullman. Anybody?
Yes.
I have probably what is a dumb question, but I'm curious about it. So, what's the downside of having magnesium contamination in struvite? Because you said if you raise the pH to 8.7, you have potential magnesium being precipitated out. So why would that be?
So it's just that magnesium phosphate is not, if you were trying to take this struvite and all that phosphorus you've removed from the manure and use it as a fertilizer, the magnesium phosphate is not really going to release that phosphorus back into the soil once you apply it. So you would rather have it in the struvite form to be a fertilizer that the plant, in a form the plant could actually use. So that the more contamination you have, like from calcium phosphates, magnesium phosphates, less of a fertilizer value that struvite is going to be for the crop. That's the main reason you would want that. Yes.
So your triticale that you said you harvested twice, did it grow the same both times, or did you see any variation?
I definitely saw a difference in the control plants. They were having a hard time the second time around. They were definitely running low on nutrients. I think the second time around also the MAP treatments were doing a little better. As we saw, they did better in almost everything. So yeah, they were a little bit greener, a little bit taller than the struvite plants. But something I didn't mention during the presentation is that those plants then got shipped to Joe in Puyallup, and he continued the experiment for another 2 harvests to see if struvite would perform better over a longer period of time. And while I don't think there's any statistics been done on that data yet, it looked like maybe the slow release nature of struvite could come catch back up with the commercial phosphorus.
Those same pots, actually, we have new graduate students come on board from Louisiana, Aaron Mackey, and we took all those soils from those 45 pots after we've harvested everything, and we have replanted a new crop of triticale as of this morning to continue to look at seeing whether there's any difference in the release rate of the MAP and the struvite. So we should know that over the next couple of months, some additional harvest. Other questions? Well, I told you she was a good lecturer. Puyallup, Liz, you always have questions.
They're kind of like pointing.
Joe, oops, am I here? You guys hearing me?
Yep.
Yes.
Okay. This is Kevin Fullerton. Katie, I don't think we've met, but I worked with Rita Hummel, I guess 3 or 4 years ago when she did some greenhouse growing experiments with struvite and MAP here in Puyallup. And are you familiar with her work?
I feel like I looked it over a little bit,
Yeah, not
but
much.
I'm not sure I'd be able to pull specific things from
Okay.
her work.
Well, I'm only raising it for this reason. She had the same suspicion or fear that if you didn't get incorporation of the struvite and the MAP in the soil, that you'd see a fall off in phosphorus uptake. And so we made tablets for her that were very small and put those in the soil. And in her experiments, there was no fall off of phosphorus. The plants that had the tablets did just as well as those that had the ground struvite incorporated in the soil. And as a matter of fact, she took it down to, I believe, a quarter of the standard phosphorus application with the struvite, just because she was getting such impressive results with it, and still didn't see a fall off in performance. And it's just striking me that her study now is quite an outlier to the ones that you have found. Her results are very different. It didn't seem like she had this problem of uptake, and she actually went the opposite direction. She minimized the amount of incorporation and soil exposure, and it didn't seem to matter. And at the time, that didn't strike us as odd. We just thought that the plants were finding the nutrient and it was working, but now it's seeming very odd in comparison to what you have found.
Right. So when you say that you made pellets, can you describe to me how?
Look like horse pills.
Like, I mean, was struvite ground down and then
They formed them in, they actually formed them into like a spike or a
It-
pellet or a pill, so
a
they were
pellet.
like compacted. Yeah.
Right, but you're on the right path there, Kitty. Yes, it was pretty finely. I don't know that we ground it specifically, but it was pretty fine what we were using. And then we have this process in which we can turn struvite into. We can harden it. We can basically turn it into a tablet of a cement, almost like a cemented form. This is something struvite will do naturally if you add the right other ingredients to it. But the ingredients are exactly what's in struvite. What you're doing is just adding more MAP to make the crystalline water adhere to the additional elements. So it is still pure struvite in the same portions of nutrients: nitrogen, magnesium, phosphorus, but it has been modified a little bit by adding more MAP and more, what was the other thing we had to add? I shouldn't get too much into this. Basically, it's the same material. It's just been concentrated into a very hard tablet that has very small surface area. That is my point.
Yeah, don't give away all of Keith's trade secrets.
Well, exactly. I should all this.
Proprietary information.
Well, I guess my question would be what the pH of the soil was. I might have a better idea.
That would be interesting. I don't know that we were paying that much attention at the time, or she did, but I'm sure it was. I guess it was recorded. I don't know.
Potting soil.
Potting soil?
Yeah.
Is that usually about?
I've never taken a pH of potting soil, but we may need to do that.
Well, my guess would be if they're really small, then maybe you're already getting that smaller surface area interaction with the soil. But if it's also acidic, then that would also be helping it to dissolve. I don't know what the pH of the soil is. So.
Okay, other questions? Liz, you gotta have at least one.
I don't. I think you did a fantastic job, Katie, and I'm so glad you got all of those oxalic acid kits delivered to you in Pullman.
Yes. Lots of kids.
Other questions? Before we take a break and
We're typical to start talking about other things.
It's typical to